Let us now look at some of the important properties of the Laplace transforms. We use the notation that x of t has Laplace transform x of s, and x of t is the inverse Laplace transform of x of s. We use capital X to denote the Laplace transform of x of t, and this s is a small letter. Most of the properties that we are going to discuss parallels those which we had already discussed in the context of the Fourier transform. So as we go along, you compare the properties that we are discussing here with those that we discussed earlier in the context of Fourier transform. They are more or less similar except for minor variations, okay, here and there, which arise as a result of the fact that the Laplace transform concerns itself essentially with causal time functions. Causal time function means x of t is equal to 0 for t less than 0. That means we are considering a right-sided sequence. Whereas the Fourier transform deals with the functions which can exist. X of t can exist t from t equals minus infinity to t equals plus infinity. So basically that is a difference that creates some differences. Otherwise the properties are quite similar. So the first property is linearity. So the linearity property says if x1 of t has Laplace transform x1 of s with region of convergence R1, okay, that will be denoted by R1, and x2 of t has Fourier transform capital X2 of s with region of convergence R2, then you take the linear combination a times x1 of t plus b times x2 of t. So the Laplace transform of this guy, let me denote x of t is equal to x of s. This will be the same scaling factor a times corresponding Laplace transform x1 of s plus b times corresponding Laplace transform x2 of s. But now with the ROC is equal to R1 intersection R2. Okay, now therefore x of s has region of convergence at least the intersection of R1 and R2. R1 intersection R2. Okay, sometimes this intersection could be empty, or sometimes it could be like larger than, anyway this we will later say, it could be empty also sometimes. Okay, if the region of convergence is empty, then in that case x of s has no Laplace transform. Yes. No Laplace transform. Okay, so if you don't have, if the intersection is empty, that means there is no region of convergence. Empty implies no region of convergence. So whenever you have no region of convergence, in that case your x of t has no Laplace transforms. Okay, for example, if you take x of t is equal to x of t is equal to e to the minus b mod of t. This you can write e to the minus bt times u of t plus e to the plus bt times u of minus t. Right? Now what you do, you take this guy individually. E to the minus bt times u of t has Laplace transform of 1 divided by s plus b, and what is the region of convergence for this? real of b is greater than minus b. Now e to the plus bt and u of t has a Laplace transform of minus 1 divided by s minus b. Then here, I'm sorry, I wrote wrongly this one. This is real of s. Real of s is less than plus b. Okay. Now, if you look at this, terms individually, this guy has the Laplace transform of this one and ROC of this one. That means what? If you plot in the s plane, this point is minus b, so your region of convergence will be like this. Okay, minus b greater than minus b, region of convergence. And for the second term, e to the bt u of t has a Laplace transform of minus 1 by s minus b, and the region of convergence is less than plus b. That means it will be plus b somewhere else. You draw the dotted line. So this is the region of convergence. Therefore, maybe I'll draw it separately like this. This is my R1, region of convergence. For the second case, the region of convergence to the left hand side like this. This is R2. Okay. Now take the intersection of these two, then it will be, this is the region of convergence. So the region of convergence is bounded by these two vertical lines. One is at minus b and another one is at plus b. So this is the region of convergence R1 intersection R2. Now what we are saying is, suppose you take b is negative. In this expression, let's say b is negative. If b is negative, that means what? B is less than or equal to 0. Even you can take 0 also. Then in that case, let's say b equals 0, then what will happen? This guy, maybe I'll write in some other color. This guy will become now real of s greater than 0. Now in this case, real of s less than 0. That means what? One case, the region of convergence is to the right hand side like this, real of s greater than 0. Right? This is real of s greater than 0. And another one is less than 0, real of s less than 0. Less than 0 like this. Now this is real of s less than 0. Now what will happen in this case? There is no overlap. Okay. If you find the common area, this is R1 and this is R2. If you find out R1 intersection R2, then there is no overlap, empty. So in that case, x of s does not exist. Okay, you cannot find the Laplace transform. Okay, in case if you want to try to visualize the signal in the time domain, how does it look if b is less than 0? You have e to the minus bt times u of t plus e to the bt times u of minus t. Now let's say b is less than 0. That means let us assume b is equal to minus 1. Then what will happen? E to the plus t, minus into minus plus u of t, plus here e to the minus t, u of minus t. That means what? This is t. When t equals 0, it becomes 2. Okay, both are adding, no? So slowly it increases, exponentially increasing. This is your e to the t. And this side, if for this guy you put negative values, you are substituting because it is multiplied by u of minus t. So it goes like this if you plot. So both are now growing signal, growing exponential. Therefore, there is no common region of convergence if b is less than 0. It is unboundedly, it is exponentially, it is increasing. Okay, individually they have Laplace transform. If you take this guy alone, it has Laplace transform. If you take this guy alone, it has Laplace transform. But the moment you take the linear combination of these two guys, then you don't have the Laplace transform because there is no common region of convergence if b is less than 0. Okay, but if b is greater than 0, then what will happen? Then it's very simple. Like you have e to the minus bt u of t plus e to the bt and u of t, u of minus t, sorry. u of minus t. That means what? This is your x of t. Now if you find the Laplace transform, this guy has 1 divided by s plus b, where real of s is greater than minus b, and this guy has the Laplace transform of minus 1 divided by s minus b, and real of s is less than plus b. Let's say b is equal to 1 in this case. It's a positive number. B is greater than 0. So in such case, what will happen? For one case, this point is minus b, so it is like this. And for this guy, it is plus b. Region of convergence is this area. Let's say this is R1 and this is R2. If you take the intersection of these two, then you will have this is minus b, it is plus b. Your region of convergence is a strip now. Strip, and the strip is bounded by the two poles. One is minus b and another one is plus b. That is 1 divided by s plus b minus divided by s minus b. What are the poles? The first pole is minus b and the second pole is plus b. So your ROC is bounded by poles. Okay. Sometimes no, the ROC can also be larger than the intersection. Like I wrote two cases right here. Yeah, one is empty. Sometimes the ROC can be larger than the intersection. That also we can give an example. Okay, as a simple example, if you want to say, one second, you note down this point, can be larger than the intersection. That means what? Like you have a times, x of t is equal to a times x1 of t plus b times x2 of t. Now in this expression, what is the Laplace transform? It is a times x1 of s plus b times x2 of s. That's what we got it, right? Now what you do, you assume that a is equal to minus b, and x1 of t is the same as x2 of t. Now what will happen in the time domain? A times x1 of t, b is replaced by minus a, or you can replace minus b here. Either way, okay. Minus b x1 of t x1 of t is equal to x2 of t, then plus b times x2 of t. Then this and that will get cancelled. Similarly, in the right hand side also, minus b times x2 of s plus b times x2 of s. Now individually they have region of convergence R1, but the moment you take the linear combination, then the region of the entire, because it is 0, the Laplace transform is 0 in the output domain. So in this case, the ROC is the entire S plane. You can take any value after it is 0, right? Okay, so ROC of x of s is the entire S plane in that case. The ROC associated with a linear combination of terms can always be constructed by using these methods. Okay, now let us take one simple example on this. Let's say example, x of t is equal to x1 of t minus x2 of t. Okay, now the Laplace transform of x1 of t is x1 of s, which is given by 1 divided by s plus 1, where real part of s is greater than minus 1. And x2 of t, if you take the Laplace transform, you will get x2 of s, and this guy has 1 divided by s plus 1 times s plus 2. Now here the ROC is real of s is greater than minus 1, right? Now what is x of t? X of t is x1 of t minus x2 of t. Therefore your x of s is equal to x1 of s minus x2 of s. That means 1 divided by s plus 1 minus 1 divided by s plus 1 times s plus 2. So if you rearrange the terms, then it is s plus 1 divided by s plus 1 times s plus 2. That is 1 divided by s plus 2. So there is a pole zero cancellations. This numerator term and the denominator term will cancel each other. Okay, so thus in the linear combination of x1 of t and x2 of t, the pole at s is equal to minus 1 and the 0 at s is equal to minus 1 cancels each other, okay, is cancelled. Therefore the pole zero plot for x of s is equal to x1 of s minus x2 of s is individually how does it look? Individually for x1 of s it is minus 1. It is the region of convergence for x1 of s. Similarly for x2 of s, what is a pole zero plot? It has two poles, minus 2 and minus 1, but this is my ROC, minus 1. Okay. Now the moment you combine these two ROC, then the two poles will get cancelled. Sorry, the pole at s equal to minus 1 will cancel with the 0 at s equal to minus 1. So finally you will end up with the s plus 2. In that case, your region of convergence is larger than the original intersection. Okay, the first one is x1 of s, this is x2 of s, pole zero plot. Then this one is x1 of s minus x2 of s. Okay, so the ROC for x1 of s minus x2 of s includes the intersection of R and R2, which can then be extended to be bounded by the pole at s equals minus 2. Okay, so the intersection of the ROCs for x1 of s and x2 of s both are greater than minus 1 and greater than minus 1. However, if you add these two guys, x1 of t and x2 of t, then ROC is always bounded by a pole or infinity. But in this case, in this example, the ROC for x of s can be extended to the left to be bounded by minus 2. So that's what we put minus 2 here. Okay, so the general rule is ROC should be bounded by either poles or infinity. Okay, when I say the ROC is like this, then it is bounded by a pole here and the infinity in the right hand side. So therefore the ROC is in between the pole and infinity. So in this case it is bounded by minus 2 and in the other side it is bounded by infinity. Okay, so that's all about the linearity property. And then let us talk about differentiation property. Okay, so differentiation in time domain. Differentiation in the time domain. Okay, so we ask a question that if x of t has Laplace transform x of s, then what is the Laplace transform of derivative of x of t has? So this is a question that we would like to ask. Now let us say the x of t has a Laplace transform x of s with the ROC R, then this guy is equal to, what is the condition that we will derive now? Okay, so the answer is s times x of s with ROC same R. So there is no change in the region of convergence. Okay, so this is the property that we will generally use for bilateral Laplace transform. Okay, but in the case of unilateral Laplace transform, the definition slightly changes. Okay, so this is the question which we would like to answer now. So given that x of t has the Laplace transform x of s, we will like to now x of s, then what is the unilateral Laplace transform d by dt of x of t when the input signal x of t is differentiated. So in this case, s times x of s minus x of 0 minus, we will derive this. Okay, this is very easy to derive. The first one is very easy to derive, and this one is unilateral Laplace transform. Okay, now assuming that the Laplace transform of a differentiated function exists, then we set up the defining integral from 0 minus to infinity of d by dt of x of t times e to the minus st times dt. So d by dt of x of t e to the minus st and dt, and the limit is, let's say, 0 minus to infinity. Now this would be the Laplace transform of the derivative of the function x of t. Now this can be integrated by parts, udv method. So uv minus integral of v du. udv is equal to uv minus integral of v du, integration by parts. So this is equal to x of t e to the minus st, and the limit is 0 minus to infinity minus integral of 0 minus to infinity x of t times minus s times e to the minus st and dt. Okay, so when you substitute these two limits in the first expression in the ROC, as t goes to infinity in the upper limit, as t goes to infinity, then x of t times e to the minus st goes to 0. That's what we mean by, otherwise the Laplace transform does not exist. Okay, so it should give the finite value, it should converge. So that is a definition of the value of s that we are going to take in the ROC. Therefore limit t goes to infinity x of t times e to the minus st, which goes to 0. Therefore 0 minus, substitute t equals 0 minus x of 0 minus, then e to the 0. So this is the first part, minus, you bring this s outside, so minus times minus it becomes plus, plus s times 0 to infinity x of t e to the minus st times dt. Okay, then this is equal to minus x of 0 minus plus s times, and don't you see this is the precisely the definition of Laplace transform of x of t. So L of x of t, you can rearrange this, L of x of t, let me write capital X of s minus x of 0 minus. Therefore the first derivative of x of t has a Laplace transform of s times x of s minus x of 0 minus. So this is an important result that we use repeatedly in solving networks problems. Okay, now this relation is assuming that x of t that we are talking about, like x of t is equal to 0 for t greater than or equal to 0 or 0 minus. Okay, that means when we are talking the derivative of the function of time, we take into the account the variation of x of t from 0 minus onwards. Often we would like to find out the Laplace transform of derivative of x of t from t is greater than or equal to 0 plus onwards. That means we disregard the jump at t equals 0. Okay, that means any jump that this function has got in transiting from 0 minus to 0 plus, we would like to exclude. Okay, we want to disregard. Mostly we always consider 0 minus, but sometimes we may not interested in what is happening from 0 minus to 0 plus. That means basically if you have an impulse at t equals 0, you just disregard when you take the differentiation. Okay, so we would like to disregard whatever is happening before t equals 0 plus. In such a case, your dy dt of x of t becomes s times x of s minus x of 0 plus. Okay, so this is the condition where we would like to consider only t equals 0 plus onwards. Sometimes no, I want to know what is happening from t equals 0 minus onwards. Then d by dt of x of t has Laplace transform. Then s times x of s. You take the initial condition at 0 minus. That's it. Nothing difficult in this. So t equal to 0 minus onwards. That is the only difference. Okay, so we are talking about the Laplace transform of the derivatives starting from 0 plus in this case and 0 minus in this case. No other difference. So the meaning of this will become clear as we take an example. So in the literature you find the Laplace transform of derivative of the signal x of t, okay, which is either written in this manner. The first one, let's say equation 1 and equation 2. Okay, so in this manner or in this manner, both are correct. Okay, first one and second one, both are correct. You can take any one depending upon whether you want to consider the derivative starting from 0 minus or 0 plus, whichever you like it. Both are one and the same. Now let me consider an example. Okay, now let me take x of t is equal to a unit step function u of t. So the signal is 0 up to this point and suddenly it jumps like this. This is my u of t. Now let me say that I want to find out the derivative of x of t. Let's say x of t is equal to u of t. Okay, so find out the derivative of x of t for t is greater than or equal to 0 minus. So there is 0 minus point here. So I'd like to take the derivative of this function starting from 0 minus. So as we take into account the variation of x of t starting from 0 minus, that is from 0 minus to 0 plus, it goes jump. Okay, it goes through a jump of plus 1. See, this point is 0 and this point is 1. So at 0 minus, your x of 0 minus is 0. At 0 plus, your x of 0 plus has the value of 1. So 0 minus to 0 plus, it goes through a jump of 1 unit. So the derivative of this function will be an impulse. Okay, because it is jumping from 0 to 1. So del of t. Therefore x dash of t is equal to del of t. So the derivative is infinite in this case. So when you integrate with the impulse, you get a rise of a step of 1. So this already we have discussed. Therefore the derivative describing the behavior of the function u of t from 0 minus to 0 plus as an impulse. And from t equals 0 plus onwards, there is no derivative, right? If you look at this function from t equal to 0, t equals 0 plus onwards, there is no derivative, no change, it is constant. So if you take the derivative of a constant function, then it becomes 0. It is a flat function, so that the derivative becomes 0. Okay, now on the other hand, if you consider the derivative only from 0 plus onwards, suppose this is my x of t, I would like to find out x dash of t starting from t greater than or equal to 0 plus onwards, then what will happen? Then it will be a constant line, there is no change. See, up to this point it is constant, so 0, and from 0 minus to 0 plus there is a jump that we don't want, but 0 plus onwards again it is constant, therefore again it is constant. Okay, for all negative values of time we assumed that the function is 0, therefore x dash of t is identically equal to 0, and for x greater than 0 it is 1, x of t is equal to 1 for t greater than 0, that means what? T greater than or equal to 0 plus. So if it is 1, if you differentiate x dash of t, then again it is 0, therefore this also 0. So when t less than 0, your x dash of is equal to 0. When t is greater than 0, 0 plus, then x dash of t is again identically equal to 0. Okay, so the Laplace transform, and we know that we already derived the Laplace transform of unit step function u of t is 1 over s. Now we will ask the question, what is the Laplace transform of, let's say x of t is equal to u of t and x dash of t time t greater than or equal to 0 minus, what is the Laplace transform? Okay, now you must use the formula. Take the Laplace transform of x dash of t greater than or equal to 0 minus, so this is equal to s times x of s minus x of 0 minus. So this is the formula that we have to use. We want to take the derivative starting from t equals 0 minus, therefore you write s times x of s minus x of 0 minus. Now what is x of s? X of s is a unit step function, right? This one, x of s equal to 1 over s. So therefore I write down here s times 1 over s. Now what is the value? What is the 0 minus value of this x of t? This is my x of t. It has a jump in this point, and now this is my 0 minus. Now what is the 0 minus here? 0, because when 0 minus there is, it stays at 0 point, and 0 plus onwards it is 1, therefore this will be 0, so it is going to be 1. And we know that the Laplace transform of unit impulse function is 1, right? What is this left hand side? The left hand side is the Laplace transform of x dash of t. X dash of t is a del of t. What is the Laplace transform of del of t? 1. In the right hand side also I have 1, so both are equal. Okay, on the other hand, if you want to consider the derivative to be one which has a value from t equals 0 plus onwards, then we use this formula, Laplace transform of x dash of t, t is greater than or equal to 0 plus, then this is equal to s times x of s minus x of 0 plus. Now what is the derivative of the function when t greater than or equals plus greater than or equal to 0 plus? Then it is 0. It is a constant function. It is constant. So this is a point which is 0 plus onwards. If you take the derivative from 0 plus onwards, then it becomes x dash of t is equal to 0. So on the right hand side, s times x of s is 1 by s, because x of t this is. If you take Laplace transform of unit step function, you will get 1 by s minus, what is the value of x of 0 plus? At 0 plus the value is 1, magnitude is 1. So you substitute 1 here. So s times s it get cancelled. 1 minus 1 which is equal to 0. In the left hand side Laplace transform of 0, that is 0. So both are equal to 0. Okay, so that's it. So that is a distinction between these two formulas. Okay, one is x dash of t greater than or equal to 0 minus, and another one is x dash of t is greater than 0 minus 0 plus. So depending upon how you want to take the derivative, whether you want to consider the derivative from t equals 0 minus or t equals 0 plus. So you can use either of this, and the difference between these two will be the Laplace transform of an impulse if there is any existing at the origin. Now let us proceed further and consider the second derivative of this function. That means x d squared over by dt squared. Now what will happen in this case? Okay, now the second derivative is after all the derivative of x of t, right? So you can write d by dt of d times first derivative of x of t. I can write like this. And we know the formula for this guy, Laplace transform of the first derivative. So apply the formula which we already know. Like d by dt of x of t is s times its Laplace transform x of s minus the initial condition of x of t. Similarly, here also what you do, this is after all s times the, one second, let me write, this is very easy, important point so that you will remember this. So now what is this one? This one is s times Laplace transform of this guy x of t minus x of t evaluated at t equals 0 minus, right? Now here what you do, again the same s comes here, multiplied by Laplace transform of this guy d times x of t by dt minus this function derivative. See this x of, let me change the color, same x of t you put and evaluate at t equals 0 minus. Similarly, you take this guy d times x of t by dt, evaluate at t equals 0 minus. Okay, now s times this s is coming here. Then you know the Laplace transform of d by x of t by dt, this we already know. What is that? S times x of s minus x of 0 minus this guy will come here. What is that? X dash of 0 minus. The derivative is evaluated at 0 minus. Now you multiply this s inside, s squared times x of s minus s times x of 0 minus derivative of x of t evaluated at 0 minus. This is normal x of t, normal, and this one is derivative. That is a difference. Okay, therefore the general formula is s times the Laplace transform of d by dt of x of t minus the value of the derivative dx of t by dt at t equals 0 minus. Okay, so that's what we wrote there. Therefore finally d squared over x of t by dt squared, you take Laplace transform, then you'll get s squared x of s minus s times x of 0 minus x dash of 0 minus. That's it. So the Laplace transform of the second derivative of the time in terms of the Laplace transform of original function is given by using this formula or given in this manner. Okay, and this can be continued, so a general formula of the Laplace transform of the nth derivative can be written as follows. So d to the n x of t divided by d to the n. See, here you have square terms, so here also square term, so substitute the same thing. Therefore this is equal to s to the n x of s minus, then there is a term, the power is 1, that is 1 less than the 2. Therefore here it will be s to the n minus 1 x of 0 minus s to the n minus 2. Then if you look at here, this is s to the 2 minus 2 I can write here, okay, because the coefficient is 1 in the derivative. Therefore s to the n minus 2 x dash of 0 minus, plus it keep on goes, and finally you stop at x to the n minus 1th derivative of 0 minus. See, here we have second order derivative. Therefore once you derivate first order derivative and evaluate at t equals 0. If you have nth order derivative, then you stop at n minus 1th derivative and substitute t equals 0 minus. Therefore we don't have to remember this formula. All we should know is the formula for the first derivative, and then one can interpolate in this fashion. In fact, you can easily get this by repeating the application of the derivative formula. Okay, so till now we have discussed how differentiation in the time domain carries over in the transform domain. So on the left hand side is time domain, the right hand side is called Laplace transform domain, or simply we can say transform domain. Okay, in the transform domain you simply multiply s times x of s. So therefore the differentiation becomes a simple algebraic equation. Okay, so it is very easy to manipulate. Now let us look at the application of this differentiation property. So this is very, very important from the system point of view and the circuits point of view. Okay, so now let us look at the application of this. This application is important in the sense that the result that are going to get here will be used over and over again in our system analysis. Now let us consider an inductor. It is L Henry. Okay, and this inductor is carrying a current, let me denote by I of t. Okay, and the voltage drop across entering point is positive and leaving point is negative. So the voltage drop is VL of t. Okay, so the voltage across the inductance be VL of t. So these are the two terminals of the inductor. Let's say this is A and B, two terminal device, and you have a current I of t which is passing through L and generating the voltage VL of t. Now the fundamental rule relating the VL of t and I of t in time domain is VL. Recall from your physics, VL of t is equal to L times di of t divided by dt. Okay, now if you know the Laplace transform for the current I of t, then we should be able to find out the Laplace transform of the voltage VL of t, because we know the different differentiation property from Laplace transform, just we studied. Now what we say is, assume that I of t has Laplace transform capital I of s, small s. So if you take the Laplace transform for the left hand side and the right hand side respectively, then both are equal. And let us assume VL of t has Laplace transform. Let me say this is small v. Okay, so small VL of t let's say this is VL of t, small v, then capital V L of S, because I want to reserve the capital letter for my transform domain. That's why I changed from small letters to capital letters. So in the transform domain we always use capital letter, but this variable is small letters. Please remember this, don't write anything wrongly. Now apply the differentiation property. VL of t becomes capital V suffix L of S. In the transform domain it becomes L times what? S times I of S minus, you evaluate the current, small I of 0 minus. So this is equal to SL times I of S minus L times small I of 0 minus. So this is the voltage in the transform domain. This one is voltage in the time domain. And this one is voltage in the transform domain or S domain. Okay, so there are 2 points to be noted here. Time domain quantities are given lowercase letters, lowercase letters, I mean small letters. When you make Laplace transform of that, we use capital letters. Okay, so these are the convention. Okay, so we should follow it. Secondly, we are interested in finding out VL of t starting from 0 minus onwards. Okay, so there is a possibility that I of t jumps from 0 minus to 0 plus. So if you want to take the derivative of that current, including the transition from 0 minus to 0 plus, then we must take into account the initial condition at t equals 0 minus. On the other hand, if you are interested in the behavior of the voltage from t equals 0 plus onwards only, then you would like to consider all values of VL of t. Okay, 0 minus to 0, then we have to take this I of 0 plus, not I of 0 minus. But we are going to illustrate this taking 0 minus values. Okay, so hereafter we always talk in terms of 0 minus t equals. Don't confuse with t equal to 0 plus onwards. That is the safer side of considering t equals 0 minus. Therefore, the more general solution will be VL of S is equal to SL times I of S minus inductance L I of 0 minus. This is a more general form. So this equation tells us that if you know the Laplace transform of current which is I of S, you can calculate VL of S in this manner using this equation. But to do this, we must know the initial value of the current. So this is the initial value of the current. Before you switch on the circuit, there are certain amount of current which is flowing in the circuit or flowing in the system, that is called initial current. So therefore we can invert this expression and find out the I of S. In case if someone wants to find out the I of S, then you can find out VL of S plus L times I of 0 minus is equal to SL times I of S. Now what is I of S? I of S is equal to 1 by VL of S divided by SL plus that L and L get cancelled, then I of 0 minus divided by S. So this is the current which is flowing through the inductor. So that gives you an alternate expression relating the terminal current and the terminal voltage in the Laplace domain. So both these equations now are the terminal equations of an inductor in the transform domain. One is in terms of voltage and another is in terms of current. You can use any one. Let me call this is 1 and this is 2. Okay, this 1 and 2 are the terminal equation of an inductor in the time domain and transform domain respectively. Okay, both are equivalent to each other. Okay, notice one thing, that the derivative operator is removed here. Okay, we don't have derivative operators. There is no more derivative operator. These are purely algebraic equations. So whenever you have a differential equation, that differential equation is converted into a purely algebraic equations. However, the extra term is that you need to have here is the initial conditions in the inductor. So these terms. Now, provided that the initial conditions are 0, then suppose I of 0 minus is equal to 0, then this relationship will be very, very simple. Okay, so this first relation becomes VL of S is equal to SL of I of S, right? So what is I of S now? I of S is equal to VL of S divided by SL. That means there is a kind of generalized impedance to the current flow in the transform domain. If a current I of S passes through an inductor, the voltage is SL times I of S. So Ls can be regarded as the generalized impedance. Like we know the formula, right? V is equal to I times R, right? So this is current and this is voltage, and voltage is nothing but current is multiplied by R. Same kind of relationship we are getting here, right? VL of S is equal to, instead of R I have SL times I of S. Therefore I can call this guy as impedance. So impedance you multiply by current, then you'll get the voltage. Therefore SL can be regarded as the generalized impedance of the inductor in the transform domain. So whenever you have an inductor, if you want to find the impedance offered by the inductor, let's say ZL, this ZL is denoted by SL. This is the amount of impedance offered by an inductor. Similarly, what is your I of S? I of S is equal to 1 over SL times VL of S. So this 1 by SL can be thought of as a generalized admittance. Okay, because admittance times voltage is the current. So the impedance concept, the proportionality relationship between voltage and current in whatever domain you are talking about, I mean transform domain or in the current domain, or even in the Fourier transform we said j omega domain or sinusoidal circuit state situation, all are valid, provided you don't have this extra terms I of 0 minus. If you don't have these guys, then these all are one and the same. That means if there are no initial conditions, then there is a proportional relationship between the voltage and current in the transform domain. So this is a proportional relationship, provided that your I of 0 minus is equal to 0. Okay, so these initial conditions spoil the character. Whenever this I of 0 minus is not equal to 0, then you don't have this kind of relationship. VL of S will not be equal to SL times I of S. Okay, so this initial condition spoil the relationship, I mean proportional relationship. Now let me again write down this equation with the initial conditions. So VL of S is equal to SL times I of S minus L times I of 0 minus. Now this thing can be represented in terms of figure, okay, by means of a circuit representation. Okay, so we have an inductance L, okay, and okay, we can think of that having a generalized impedance. Now this generalized impedance is SL, and current flowing through this is I of s through it. Okay, not the raw current, it is not I of t, but it is I of s, that is the transformed current. And across the terminal of the inductor we must have a voltage VL of s. Okay, so VL of s, but this voltage, this is a voltage across the terminal of the inductance. We know that VL of s is simply SL times I of s. Okay, minus there is one more additional term, L of I of 0 minus. So this current I of s passing through LS, this generalized impedance, will develop voltage which is SL times I of s in the transform domain. But to complete the picture, I have one more terms here, minus L times I of 0 minus. Therefore what you do, you put this figure is not complete. So what you do, you take the same inductor, then this component has to come. So therefore you put minus here, and this is plus, and this is L times I of 0 minus, your initial current, and this is the generalized impedance SL, and current flowing through this is I of s. Now this whole thing becomes what? Your VL of s. Okay, and this L times I of 0 minus is independent of what? I of s. It is an independent quantity. Okay, that is equivalent to voltage source. So this whole thing will be equivalent to a voltage source. So you must have a voltage source in the transform domain, and that voltage source value is this guy. Okay, and this voltage source value is L times I of 0 minus. Therefore VL of s can be thought of as I of s passing through SL, okay, that generalized impedance, and developing a voltage SL times this voltage, SL times I of s, plus minus of this voltage, L times I of 0 minus. Okay, similarly, if you want to model this equation by means of an equivalent circuit representation, we have an element having a generalized impedance SL with a terminal voltage VL of s. Okay, so that is I of s is equal to VL of s divided by SL plus I of 0 minus divided by s. Now what you do, you have an inductor L, and the generalized impedance is SL, and this voltage across this guy is VL of s. Okay, now the current flowing through the circuit is I of s. Now this I of s is not only this term, you have an additional term, this guy. Okay, therefore, okay, so instead of I of s times 1 over SL, by the way, what is the current? This current flowing through this current VL of s divided by SL. This is the current flowing through this path, this branch. But in addition to this VL of s divided by SL, I have one more current. So therefore you put a parallel branch in this manner. Like this. What is this value? This value is I of 0 minus divided by s. Okay, so this is another representation. Another equivalent representation. Okay, so another equivalent representation of an inductor in the transform domain, S domain. So we have an inductor having generalized impedance SL in parallel with the current source. This is the current source. So impedance and parallel with a current source, and the generalized impedance is SL, and the current source is I of 0 minus divided by s. So you have two equivalent circuits for an inductor. which incorporates the initial value of the current. Okay, and that initial value of the current is if0 minus, and both these are called transform diagrams pertaining to an inductor. So either you can use this diagram or you can use this diagram, okay, depending on the application what you are using. Okay, so one incorporates the voltage source, the other incorporates the current source, and here we have voltage source and here we have current source. So depending upon your convenience in a circuit analysis problem, you flavor the use of voltage source, you use this. On the other hand, if you are allowed to with a current source, you can use the second one. Okay, like whether you are employing Kirchhoff's voltage law or Kirchhoff's current law, so based on that you can choose any one which is relevant to you. Okay, I mean in particular if you have a network in which the node equations are preferred method of solution, maybe you would like to have a current, but both are equivalent, either use this method or this method. The important thing to keep in mind is that the terminals of the inductor in the actual circuit are A and B. One second. In the time domain, this is A and B. Okay, but in the transform domain, the terminals are same terminals, but you have a voltage source here. Again, this is A and B, but in between you have a voltage source like this, and like this. This also A and this also B. Okay, so we should not think that the terminals of the inductance in the transform diagram are no, these two like this. Don't think like this. Okay, don't think these two are the terminals. The actual terminal is this guy and this guy in the transform domain. Here also the actual terminal is these two guys. Don't take this and that this is wrong. Okay, so what we have done here is the representation of an inductor in the transform domain, where the variables in the circuit are the transformed variables, not the functions of time. Okay, therefore VL of S is a Laplace transform of the voltage, and IL of t is the again Laplace transform of the current. So the variables are transformed variables, and the element strength is not L, it is SL. See, originally here it is L and here it is SL, and here also it is SL. Okay, so in the transformed domain the element strength is SL. Okay, and this SL is called the generalized impedance of an inductor in the transformed domain. That's it. Okay, in a similar fashion we can give similar representations for the capacitor also. Okay, with an initial charge on that. Okay, that we will postpone, okay, a little later. We will not do this now itself, okay, in great detail at this point of time. Okay, just like we have a generalized impedance SL for an inductor, for a capacitor it turns out that generalized impedance, which is 1 over CS or 1 over SC. Okay, it turns out that the generalized impedance is 1 over SC. We will do that a little later, but our point in presenting this at this stage is to show an application of the derivative rule in the Laplace transform theory. How your derivative property can convert a differential equation into an algebraic equation. Okay, that is how we can apply that to evolve the circuit model of this type. So these are called application of your differentiation property of your Laplace transform. Okay, so let me stop at this point. We will continue from this point onwards in the next class. Probably we will start with the multiplication of a signal by time t. Okay, let me stop at this point. Thank you very much.